Happy Thursday to you all. Last seminar before fall break. So Monday and Tuesday we have a fall break, but Thursday we'll be back here for science seminars next week. So I'm glad to hear you guys all excited about your break coming up, discussing where you're going, what you're going to do, right? What great adventures you're going to have to share with us when you come back again next week. So that'll all be good. But before you go, before the break, we have with us here to give us a science seminar today, Mr. Isaac deJager. Whenever I see Isaac, I think of his brother Connor. Is he here? Hey, cool. I see. Right. Stand up.
I get the spotlight today.
Yeah. So anyway, he's going to tell us about some work that he's been doing on generalized Motzkin paths.
Motzkin.
Yeah, makes me hungry. Motzkin sounds like something to eat, doesn't it? Yeah. And remind you that we'll have lunch after the seminar, so if you want to hear more about how Isaac did this work and all this kind of stuff, come join us for lunch. We'll be in the Joyce room of the corner cafe. All right, let's give Isaac a round. Thank
you. So yeah, if you guys don't know me, I'm a junior here at LeTourneau University, mathematics and computer science major, because math and computer science are both really rad. I get the opportunity to talk to you guys about what I did last summer. I participated in a research experience undergrad, or an RAU, so I got the opportunity to conduct original mathematical research, which was a tremendous amount of fun for me. I loved getting to do this. I got to work at Valparaiso University, which is in Valparaiso, Indiana, far northeast Indiana. It's about an hour away from Chicago. I worked alongside two other undergrad students, Madeline Knockin and Frank Seidel, which is why their names are up there, under the advisorship of Dr. Paul Druby, who's a professor at Valpo. They reached out to me and was like, hey, you want to come to Valpo and come research math? And I was like, heck yes. So that's what I did for about 2 months, conduct original mathematical research in combinatorics. If you guys don't know what combinatorics is, that's okay, because I didn't really know what combinatorics was either prior to this last summer. I kind of like to think of it as combinatorics is the math of counting things. It's basically you construct a lot of different sequences, and you compare different sequences to each other. And our group studied a specific combinatorial construct called Motzkin paths. So whether you guys are here because you're just interested about math, or whether you're here just to get extra credit, I like to thank you guys all so much for coming, because I'm so grateful to get the opportunity to talk to you guys about my math research, because this stuff to me is pretty cool. It may not be cool to all of you, but I don't know, math is pretty legit. So let's talk about Motzkin paths. So before defining what a Motzkin path is, I need to define something called a lattice path. So if you consider like an XY plane, a lattice path is simply like a series of line segments that starts at the origin, and each line segment has endpoints of integer coordinates. So this is just a short example of a lattice path. You notice that these line segments can have any length. They can go anywhere they want. It's a pretty simple construct. And a Motzkin path specifically is a type of lattice path with a few restrictions. So a Motzkin path is a lattice path that starts at the origin 0, 0 and ends at the point n, k, meaning that it has n steps in the whole path. There are only 3 types of steps that you can use in a Motzkin path, and that's an up step, a level step, and a down step. So to represent that, we can see our up step goes 1 to the right and 1 up. So it just kind of looks like that. And then a level step is just level, so ta-da. And then the down step goes 1 to the right and 1 down. So all of these steps move the Motzkin path 1 further to the right. So because they all move it 1 to the right, that means that the number of steps that you have, or n, if you have n steps in your Motzkin path, the x-coordinate that it ends at is going to be n, right? And then the height k just tells us where the Motzkin path has to end. Now, most Motzkin paths that we dealt with, we studied Motzkin paths that mostly just ended at height 0, meaning that they start on the x-axis and they end on the x-axis. But where did I put my clicker? But they can get a little bit more complicated. So we denote the set of all Motzkin paths of any length n and height k using this script m. and the number of Motzkin paths of length n and height k, we denote with this just regular n. So here's a couple examples of Motzkin paths. This first one, we see that the length of the Motzkin path is 3, meaning they're all composed of 3 line segments. We are also told that the height of the Motzkin path is 0. So note that they all start and they all end at height 0, or on the x-axis. There are 4 different ways to draw this Motzkin path. There are 4 distinct ways to draw this Motzkin path, because there are only 3 types of steps, right? Level steps, up steps, and down steps. Sounds pretty simplistic. This second one has the same length, but now we're ending at height 1. So all of these Motzkin paths now have to end at height 1, and there are only 5 ways to draw Motzkin paths of height 1. So that's how we denote that variable n, 3, 1, we're saying is equal to 5. And that's basically just what a Motzkin path really is, but the majority of our research, we generalize Motzkin paths to make them more complicated, because, you know, what's math without complications? Okay. So the Motzkin triangle is a tool that we've used to help figure out the number of Motzkin paths of any length n and any height k. For example, like we saw before, we saw m of 3, 0 is 4 and m of 3, 1 is 5. So if we wanted to find m of 4, 2, I mean, one way we could find that is just by drawing them all out, right? We could just draw every single Motzkin path of length 2, or length 4 and height 2, but that can take some time, especially for high magnitudes of n, and, you know, we could miss one. So that's not a very effective strategy. So we use this thing called the Motzkin triangle. And the Motzkin triangle is an infinite, 2-dimensional lower triangular array. It's this triangle that stretches all the way down to infinity, where its index is specified by n, k, or the height, or the length, the height. We start counting n and k at 0, so each column of the triangle is the row, or n. Each row of the triangle is n, the length, and each column is the height, or k. And we start counting n and k at 0. So this first one that's here on the top here, that is the number of Motzkin paths of length 0 and height 1. The number of Motzkin paths of length 0 and height 1, which is just a dot. It's a Motzkin path that has no length, so it's composed of no line segments, so it's just a dot. And there's really only one way to draw a dot. Kind of looks like that. So this, if we go down one row, we get to another one. That is the number of Motzkin paths of length 1 and height 0. Length 1 and height 0. So that's just a straight line segment. The only way to draw a Motzkin path of length 1 and height 0. If we go down one more row, we get 2. That is the number of Motzkin paths of length 2 and height 0. There are 2 ways to draw that. 2 level steps, or an up step and a down step. Hence we have the value 2. And you can keep going anywhere you are in the triangle, and that is the number of Motzkin paths for any length n and any height k. So it's a very helpful tool. So if we go back to this guy, remember we start counting n and k at 0, so when n is equal to 4, that is the 5th row. We're on the 5th row, k is equal to 2, so that is the 3rd column, and that gives us 9. And that's far more convenient than drawing out every single Motzkin path. So this is a very helpful tool for us, but it may be a little bit confusing about how we get the Motzkin triangle. We actually calculate the Motzkin triangle using recursive formulas. So each row is calculated by using the row directly above it. And there's 2 different formulas for doing that. The first formula refers to all elements that are in the first column, that first primary column. For example, we get 4 by adding up 2 and 2, the 2 elements in the row directly above it. We get 9 by adding up 4 and 5, etc., right? Every single element that isn't on the first column, we have to sum up 3 elements in the row above it. So you'll notice 5 is equal to 2 plus 2 plus 1. And 12 is equal to 4 plus 5 plus 3. And these recursive formulas just continue and generate an infinite triangle for any length n and any height k. There are good reasons as to why these recursive formulas work. I would really love to talk to you guys about the proof about that, because I think it's pretty intuitive, or ingenious, rather. But I'm afraid I don't really have time to talk about that today, but I would really love to. So if you guys have questions about that, just please let me know. So yeah, so the reason why we care about the Motzkin triangle primarily is because, we can find the length, the number of Motzkin paths of any length and any height. Another reason why we care about the Motzkin triangle is that we can generate sequences out of it. And that is what combinatorics is pretty much all about, is sequences, sequences, sequences. So I pulled the first column out, and that sequence is referred to as the Motzkin numbers. If we keep on stretching this triangle down, we'll notice that that first column continues 21, 51, 127, etc. And that is an infinite sequence. That sequence counts the number of Motzkin paths of any length n and height 0. So yeah, that's Motzkin triangle. Ta-da. Okay, I'm going to have to deviate a little bit before moving on to Motzkin paths again. I need to define another term called Rearden arrays. And a Rearden array is, well, the Motzkin triangle is actually an example of a Rearden array, and I'll explain why in a little bit. But a Rearden array is essentially just, you have your integer triangle, and if the integer triangle has an A sequence and a Z sequence, it is a Rearden array. So what are A sequences and Z sequences? I know these definitions look kind of bizarre. I kind of have to include them up there because they're the formal definitions, but I know they don't really make a lot of sense. So a Z sequence is used to calculate the first column of any integer triangle. If every single element in the first column is equal to some sum of the elements of the row above it, where each element in the row above it is multiplied by a constant, then this integer triangle has a Z sequence. We determine those constants via Z0, Z1, Z2, etc. And you may notice these powers of t here. The powers of t refers to where on the row we are. I know that's confusing. I'll show an example in a second. And then A sequence is similar, except we're now looking at every element that isn't on the first column, right? If you're looking at an element that's in the second column, for example, if that element in that second column is equal to some sum of the elements of the row above it, where each element is multiplied constants A0, A1, A2, etc., then the sequence has an A sequence, right? And we denote that again using A1 or A0 plus A1 times t plus A2 times t squared, where the power of t tells us where on the row we are. And if an integer triangle has an A sequence and a Z sequence, it's a Rearden array. So here's an expanded form of the Motzkin triangle. As we talked about before, the recursive formulas to create the Motzkin triangle hold true wherever you are in the triangle. So that first column we find by summing up the two elements of the row above it, right? So 9 is equal to 4 plus 5. Or 9 is equal to 1 times 4 plus 1 times 5. So our constants Z0 and Z1 become 1 and 1. Hence our Z sequence for the Motzkin triangle is Z of t equals 1 plus t. Or Z of t equals 1 plus 1 times t, or whatever. But we don't include any more powers of t because we're not adding up any more elements in that row. We're only adding up the first two. The A sequence, as we said, we get every element that's not in the first column by summing up 3 elements in the row above it. 12 is equal to 4 plus 5 plus 3. Or 1 plus 4 plus 1 times 5 plus 1 times 3. Hence our constants A0, A1, and A2 are all 1. A sequence becomes 1 plus 1 times t plus 1 times t squared. Now, the reason why we care about Rearden arrays is, first of all, we can use A and Z sequences to much more efficiently describe the recursive formulas of integer triangles. Because those polynomials right there are far simpler than those recursive formulas. They look a lot nicer, which is a very nice thing in mathematics to make things look pretty. But a more important reason why we care about A and Z sequences is because if we have two different integer triangles that are both Rearden arrays, and if they have the exact same A sequence and Z sequence, then they are the exact same triangle. A and Z sequences are recursive formulas that generate triangles. And if two different triangles have the same A and Z sequence, then they are the same triangle. And that is an extremely helpful fact for us when we prove some of our biggest theorems. Because a lot of our theorems that I'll show an example of one later is showing how this combinatorial construct and this combinatorial construct make the same sequence. Why? Because they can both be represented with an integer triangle that have the same A and Z sequence. So that was a strategy that we used to prove pretty much all our biggest theorems. Not all of them, but most of them. So this is why I bring up A and Z sequences, because they're very, very helpful. Okay, so let's go back to Motzkin paths. Before we just looked at the specific definition of what a Motzkin path is, but our group, we don't really care about normal Motzkin paths. We care about generalized Motzkin paths. So let's look at our first generalization, and that's coloring Motzkin paths. So this is an XY colored Motzkin path, which is a Motzkin path that has a length n and height k, but now we're allowing for more types of level steps. We're allowing for more types of level steps. So we can color these level steps using the values of x and y, and we don't really color them, we just kind of put a number above them, which I'll show an example of in a second. Yeah, I know, I wish we colored them, but it's fine. So x refers to the number of ways we can color level steps that are on the x-axis. X is the number of ways we color level steps on the x-axis. Y is the number of ways we color level steps raised above the x-axis. And then we denote the number of XY colored Motzkin paths of length n and height k using that m, n, comma k, and then colored x, comma y. So here's a couple examples of colored Motzkin paths. This first one is a really simple example. We have the exact same n and k as the examples that we had before. But this first one, we're having x equals 1 and y equals 1. What this means is that there's only one type of level step, whether you're on the x-axis or not, right? Which is why you may notice that the number of Motzkin paths is the same as it was before. The number of level steps that we have is 1. So it's pretty simple. This second one's more interesting though. We're allowing for one type of level step on the x-axis, and we're allowing for two different types of level steps above the x-axis. Which is why you may notice that these two paths right here, those two paths have the exact same shape. But we count them distinctly because we can color that level step two different ways. So what coloring does is essentially, for the majority of cases, coloring increases the number of paths that we have in our set of Motzkin paths. This Motzkin path right here, you may notice that there are 4 Motzkin paths that have that shape, but there are 4 different Motzkin paths because you can color them 4 different ways. Wow. So yeah, for larger values of x and y, you're going to get a lot more types of Motzkin paths, larger numbers. But for example purposes, I'm going to keep x's and y's pretty low. Okay, so like the Motzkin triangle, we can make an xy Motzkin triangle, which tells us the number of Motzkin paths of any length n and any height k using the unknowns x and y. So you may notice that this Motzkin triangle is in a polynomial form. This is because the numbers that go in there are entirely dependent on what x is and what y is. Also, something I may have probably pointed out, you may have noticed that this main diagonal here is entirely composed of 1s. What is that about? That's because everywhere on the main diagonal is where n is equal to k. That means the length of the Motzkin path is equal to the height. And whenever the length is equal to the height, there's only one way to draw that Motzkin path. That's all up steps. If you put a level step or a down step anywhere in that Motzkin path, then the length is never going to equal the height. That's why that main diagonal, everywhere n equals k, there's only one way to draw that Motzkin path because it's entirely up steps. That's something I should have mentioned on the previous one. We're going back to colored Motzkin paths. You may notice that we also have recursive formulas for our xy Motzkin triangle as well. And you may notice that they look a little bit different. Before, we just had every element on the main column equal to 2 elements in the row above it. Now it's a little bit different. We have x times the element directly above it plus the 1 over. So x, to get this x squared plus 1, we have to do x times x plus 1, right? In order to get x cubed plus 2x plus y, we do x times x squared plus 1 plus x plus y, which you can simplify out and we'll give you that expression. In order to get any element that's not in the first column, we have to do, to get this value, we need to do this plus y times this plus that. So we can simplify that. In order to get this x squared plus xy plus y squared plus 2, we do x squared plus 1, right? Plus, following our formula, we multiply y times x plus y, plus 1. And if you don't trust, that comes out to x squared plus xy plus y squared plus 2. You can just, I don't know, algebraically simplify that. Okay. So again, I would love to explain why these recursive formulas work. I don't have time, but just trust that they work, because they do. So yeah. Here's an example of an xy Motzkin triangle where we have x and y set constants. X is equal to 1, y is equal to 2. So we can either just plug 1 and 2 into those polynomial equations, or we can just calculate it recursively using these recursive formulas. I'm also showing here the a and z sequence for this. You may notice that z of t is exactly the same as it was before. This is because x is equal to 1. So we get 5 by doing 1 times 2 plus 1 times 3. We get 14 by doing 1 times 5 plus 1 times 9. A of t is a little bit more complicated because y is equal to 2. So we get 9 by doing 2 plus, we get 9 by doing 2 plus 2 times 3 plus 1. We get 28 by doing 5 plus 2 times 9 plus 5, right? That's the a and z sequence, and that holds true everywhere in the triangle. Something that I think is also notable here is that this z sequence, I'm going to find another board here. It's actually funny to go down. I love these boards. These are so much fun. So z of t, I'm going to write as 1 plus t to the power of 1. And you may notice a of t factors into 1 plus t squared. This is something that actually is probably going to show up later, but just notice that this is another benefit of a and z sequences. We can factor them so they look even more simple, because we like simplicity. So again, we can use Motzkin triangles again to get sequences. So this first sequence right here comes from the first primary column. And so that's handy. So because we can graph sequences out of them, this led to the first part of actual research that we did in our group. So we developed some Java programs where you input a value for x and we input a value for y. It generates an xy Motzkin triangle, and then it spits back out that first column. And that first column, if you remember, is the number of Motzkin paths of length n and height 0, color x, y. So we varied x and y between 0 and 4. So we got back a whole bunch of sequences. And then we took those sequences and went to the Online Encyclopedia of Integer Sequences, or OEIS. This is just an online website that you can just go onto. It's this giant database of thousands and thousands of sequences and descriptions about what these sequences count. So you can plug in 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus 18 plus 21, etc., and it'll spit back the Fibonacci numbers at you. It also might spit back a few other things that the Fibonacci numbers count, which is a really helpful tool for us because we can see what sequences count what combinatorial constructs. So we took the sequences that we got from these XY pairs, plugged it into OEIS, and saw if we got any matches, if these sequences count anything else in mathematics. And you may notice we got a lot of hits. We got a lot of hits. Everywhere there's a dash is where we didn't get a hit, meaning that's a unique sequence. And everywhere else is where we got a lot of matches. When we have A followed by a bunch of random numbers, that's where we did get matches to other combinatorial objects, but we didn't really care too much about them. They're just boring. But we do know that they count the same things, which is helpful to know. And then everything else, we have the Reardon numbers, fine numbers, Motzkin numbers again. That C of n is what's called the Catalan numbers. The one below that is the shifted Catalan numbers. I can talk more about Catalan numbers in a little bit, but we got everywhere else there's something that was actually more related to our project. So yeah, that was our first research project. First thing that we did via research during the summer.
Isaac, was that known that there was a connection to Catalan numbers with these arrays, or did you?
Well, our professor knew.
Oh, okay.
We didn't know yet. He led us to that point.
Okay. Because that would be really cool.
But yeah, I'll show why that's the case in a little bit. Okay, so back to Motzkin paths. We're going to look at another generalization of Motzkin paths. So forget coloring for a second. We're going to come back to it. And let's just look at normal Motzkin paths again. An order m Motzkin path is a Motzkin path of length n and height k. But it's different from a Motzkin path because now we have more steps. Now we have more steps. Before, a Motzkin path just had 3 steps, right? It just had an up step, a level step, and then a down step, right? Goes 1 to the right and 1 down. But let's say we have an order 3 Motzkin path. Now we have 2 more steps to add. We have a double down step. It goes 1 to the right and 2 down. And we have a triple down step. 1 to the right and 3 down. Okay. So the number of steps that we have in our step set is completely dependent on what the order is. And we denote the order using this m, right? And the steepest down step just goes 1 to the right and then down m. We denote the we denote the set of order m Motzkin paths using that script m, and we do that little exponential m up there. It's not really an exponent, but it looks like one. And then we denote the number of such paths using m exponent m, n comma k. Something you should probably notice here is that order 1 Motzkin paths are the same as regular Motzkin paths. Order 1 Motzkin paths are the same as regular 1 Motzkin paths. Why? Because the steepest down step is a single down step. So this step isn't allowed in order 1, and this step isn't allowed in order 1. So we just have normal Motzkin paths. That's kind of cool. Okay, here's a quick example of an order 2 Motzkin path. Notice I'm using the same value of n and k as I did before. If you remember before, order 1 Motzkin paths with a length of 3 and a height of 0, there are 4 ways to draw that. Now there's a 5th way to draw that one, because we have a double down step. This is an order 2 Motzkin path, so we can have double down steps, and that's what that last one in there is. Again, all the steps still move it 1 to the right. It's just that we're moving it, the steps get steeper and steeper. Now we can also make an integer triangle or Reardon array using order m Motzkin paths, and those are the recursive formulas to calculate that, and we could represent that A and B sequence. And those are true. They are true. Trust me, they're true. They work. Okay. Now let's color order m Motzkin paths. This right here, this definition right here. Yeah, this is fun. This right here is the crux of our research. Once we learned what this was, this is where the majority of our research revolved around, because we started relating this to other combinatorial objects. So if we color order m Motzkin paths, before we just colored level steps, right? The only steps that we allowed to color were level steps. In order m Motzkin paths, we can now color down steps. So, right, we color every single down step except for the steepest down step. So if this order 3 Motzkin path was colored, x and y, we color this guy, we color this guy, and we color this guy. We don't color that guy, because it's the steepest down step. So, we now have to have multiple x and y values, right? X refers to, x naught is the number of ways we color level steps that are on the x-axis. X1 is the number of ways we color single down steps that end on the x-axis. Y2 is the number of ways we color double down steps that end on the x-axis, and so forth. And then Y is the reverse, it's just for steps that end above the x-axis. Y naught, again, is level steps above the x-axis. Y1 is how we color single down steps that end above the x-axis, and so forth. And we use these notations. It's the same order m, except we have xy tuples to tell us that we're coloring it. Here's an example. These examples are helpful. So we have length 3 and height 0, again. It's very helpful numbers. They're order 2 Motzkin path, and it's colored, meaning order 2 Motzkin paths, we're coloring level steps, and we're coloring single down steps. We don't color double down steps, because in this example, the double down step is the steepest step. So we're having x is equal to 1, 2, y is equal to 3, 3. So there's one way to color level steps on the x-axis, which is why it's all 1. But there are 2 ways to color single down steps that end on the x-axis. So you may notice the second and third path have the same shape, but they're distinct because the single down step is colored 2 different ways, because x1 equals 2. The other thing I think we should probably point out here is how there are 6 Motzkin paths that have the same shape. 6 Motzkin paths that have the same shape. but because of x and y, they're colored 6 different ways, right? And the last thing I want to point out is just this double down step again. That one's not colored, it's the steepest down step. And yeah, that's what XY colored Motzkin pads look like. They're a blast. All right, so I'm also going to represent this using integer triangles as well. XY color, order m XY colored Motzkin pads with integer triangles. This is an easy example, order 2, where x and y are all 1. Everything is 1. This means that there's one type of level step and one type of down step, whether you're on the axis or not. And it creates this integer triangle with this specific A and Z sequence. This one's more complicated. We're using the same coloring scheme that we used in the example. You may notice that the A and Z sequence get more complicated, right? But here's something that's kind of funny. This A and Z sequence in polynomial form can also be factored. This Z sequence factors to 1 plus t squared, right? This A sequence, 1 plus t cubed. Voila. That looks pretty. Okay. So we then went back to OEIS. Actually, first we went back to our program and then updated it to allow for higher orders of Motzkin pads and to allow for more colors. And then we spat those numbers into our program. It gave us back the first column of those triangles. And then we took those sequences, put them back into OEIS. You may notice we got a lot less hits now. We got a lot less hits because these Motzkin pads are getting more and more complicated. These sequences are getting more and more distinct. But we still got some hits. Again, some regular boring ones that we don't really care about. That C at N in the third, that's what's referred to as the third Catalan numbers. You may have noticed before, as Dr. Krause pointed out, we have the Catalan numbers here, and then we have another sequence, which is the third Catalan numbers. Now, the Catalan numbers is a very famous sequence in combinatorics. Our advisor, Dr. Druby, gave us this book called Catalan numbers, and it was about like this thick or so, and the entire thing was just things that the Catalan numbers count. That was the entire book, this giant book of everything that the Catalan numbers count. So it's a very, very famous sequence that counts a lot of constructs, and we actually just showed that it counts Motzkin paths. So that's pretty cool. So we're going to look back at Catalan numbers because there are different orders to Catalan numbers. This first one is the 2 Catalan numbers, or just Catalan numbers. There's no 1 Catalan number. So this is the Catalan numbers in this sequence, right? Now, as we saw before in OEIS, this is equal to order 1 Motzkin paths, where x is equal to 1 and y is equal to 2. This second sequence is the third Catalan numbers, and as we saw in the previous table, that is when x is equal to 1, 2 and y equals 3, 3. Then we made another program where it allows you to input a sequence, so we inputted the 4 Catalan number sequence, and then it just guesses and checks values of x and y until it gets a match to that sequence. And that's the third order Motzkin paths where x equals 1, 3, 3 and y equals 4, 6, 4. So then our next job became, okay, we have to guess what x, y tuples create a sequence that is the 5th Catalan numbers. It's pretty logical to assume that it's order 4 Motzkin paths, because as we can see, the orders just keep incrementing. But unfortunately, our program would have taken hours and hours and hours to compute that because there's too many possibilities. But based on these 3 results, we tried to guess what x, y tuples it was going to be. I'm wondering, does anyone here have a guess about what the values of x and y are based on the previous examples? What'd you say?
Pascal triangle.
Oh, I'm so happy someone said it. Okay. Let's find the board. Oh, I'm so happy. Right? Hopefully you guys recognize this as Pascal's triangle. Frank was actually the one who figured this one out. I was really confused, but apparently you weren't. Okay, so as you may notice, to get the Catalan numbers, x equals this, y equals this. To get the third Catalan numbers, x equals this, y equals this. To get the four Catalan numbers, x equals this, and y equals this. So if we expanded one more row, what is x going to be? 1464. Yeah. All right, what's y?
5, 10, 25.
5, 10, 10, 5. Woohoo! So then we went back to our initial program, plugged in those values of x and y, and confirmed that the sequences do match. And then we checked that for other rows of Pascal's triangle. We went to about like the 7 or 8 Catalan numbers. So at this point, we were firmly convinced that this is how we predict what values of x and y do that. And you know, this kind of blew my mind because I was like, this is something that I learned, I don't know, maybe in like pre-algebra was when I first learned about that. It was like on a poster on a wall. So what in the world does this have anything to do with Motzkin paths? So this is really cool. So I'm going to quickly like redefine the Pascal's triangle for you. All right, I'm going to have to cut some stuff out. Sorry. Pascal's triangle isn't just like you summing up the two elements of the row above it. Pascal's triangle is composed of what is called binomial coefficients. I won't really go into too much detail about what binomial coefficients are. But basically what you can think about it as how many different ways are there to choose one thing, how many different ways are there to choose one thing out of a set of one things, right? So if you had 2 M&Ms, how many different ways are there to choose one M&M out of 2 M&Ms? There's 2. Yeah. There's a formula to calculate binomial coefficients, but this is what Pascal's triangle really looks like in its pure form. So once we had this, we could create a formula for xy tuples. So for any order, we can pull out the values of x's and y. This is what it looks like. Sorry if it's ugly. So the sequence that is formed by counting Motzkin paths of length n and height 0 with order m, colored x, y, is equal to the m plus 1 Catalan numbers when x is equal to m choose 0, that's how you refer to binomial coefficients, m choose 0, comma m choose 1, all the way through m choose m plus 1. And y is equal to m plus 1 choose 1, m plus 1 choose 2, all the way through m plus 1 choose m. Right? Because as we saw before, each pair is just summing up some number of the rows of Pascal's triangle, which is why we just increment that second term in the binomial coefficient by 1 every time. So if we run a quick example of this, if we look back at the 3 Catalan numbers, which we saw were Motzkin paths of order 2, colored x, whoopsie, y, m is equal to 2, right? So x, according to our formula, is 2 choose 0, 2 choose 1. And then we don't go past that because, as we notice here, it goes all the way up to m choose n minus 1, right? And this is 1, oh, what the heck? That's 1 comma 2, right? Y, on the other hand, according to our formula, is m plus 1 choose 1, m is 2, so that's 3 choose 1, and 3 choose 2. Which comes out to 3 comma 3. And if you don't believe that, look up binomial coefficients or something and figure that one out. So yeah, we were convinced that this theory of ours was true, right? Because we tested it as many times as we could. So we were convinced that it was true. Unfortunately, we couldn't formally prove that it was true for any order of m until about like 2 or 3 weeks later when we learn more about what the Catalan numbers are. You guys have to be out of here in 10 minutes, so I can't really explain to you how we formally prove this, but I'll explain a little bit of the sketch of proof, or the sproof of it. It's literally called the sproof. That's not a joke. So we know that the Catalan numbers count another combinatorial object called L-array paths. And L-array paths are like kind of Motzkin paths, but they look a little bit different. We know that the Catalan numbers count L-array paths. So all we had to do was show that the L-array paths create integer triangles with this A sequence and Z sequence. And once we did that, then all we had to do was show that our formulas over here for X and Y tuples also made the exact A sequence and Z sequence. So again, because these two separate constructs create Reardon arrays that have the exact same A sequence and Z sequence, they count the same thing. They are the same sequence. And because L-array paths count Catalan numbers, then so do these. And then it was proved. And it was lit. Okay. So I'm afraid that's kind of all I have time to talk to you about my research. We discussed, or we researched a lot more things. Like I said, L-array paths, that's already a predefined combinatorial construct, but we made our own generalizations of L-array paths. So by the end of the summer, we kind of defined our own combinatorial construct, and then connected that combinatorial construct to specific Motzkin paths with specific coloring schemes as well. And that was a really cool part of the summer. I'd like to, before moving on to questions, I just want to talk a little bit about REUs. I know Tatum, there she is. I know Tatum talked a little bit about REUs at the beginning of the semester, but for those of you that still don't know what REUs are, they stand for Research Experience Undergrads. It's an opportunity for you guys to conduct your own research in whatever field of science or mathematics you're in. I did a math REU, so I did math research, and it was pretty cool. But at this Valparaiso University, there were also research groups in data science. There were research groups in chemistry, research groups in physics and astronomy, right? There's so many different areas of science and mathematics that you can do research in. And there's multiple benefits to REUs, probably the most prevalent one being that you get the opportunity to see what conducting research looks like as a career. You work closely with advisors, right? People that have made this their career, so you get to ask them a lot of questions about what life is like, right? And you get to see what they do day to day. And also, we got the opportunity to tour grad schools as well. We toured Purdue University, and we toured the University of Notre Dame. And we got to ask a lot of questions to grad students there and see what life is like in grad school as well, which is really, really great. I had a lot of questions about it, and I get a lot more understanding about what life would look like should I move on and do graduate math and study math and research math as a full-time career. Another thing that I should probably point out is that we had a lot of speakers come in from different universities. They were all talking about their math research and their scientific research. And the most common question that we asked them was, what can we do now to help us get into grad school later? The answer was always the same: REUs. What you're doing right now is the most beneficial thing that you can do to help you get into grad school. So if you guys are interested in grad school for whatever field of science you guys like, I highly recommend trying to sign up for an REU. They are a great experience. They look so good in your resume. They really pop out when you're trying to apply for grad school. It is a tremendous opportunity and a really, really great experience. It's super educational and super beneficial to your career. So yeah, I guess that's my whole presentation. I like to thank a few people first. I appreciate that. I wish Dr. Ball was here because I'd really like to thank Dr. Ball for signing this opportunity up for me. I sent him my thing at the end of the summer, and he was like, "Hey Isaac, you want to do a science seminar?" And yeah, I loved presenting in front of you guys. I love getting the opportunity to talk to you about my research. I wish I had more time to explain more of it. But I'd like to thank Dr. Ball so much for doing that, and of course my partners Madeline and Frank, wherever they are in the world right now, and my advisor, Dr. Paul Julie, who's still in Indiana. And also, I'd like to thank everyone here in LeTourneau who gave me words of encouragement to do this, because I'm not going to lie, I was really nervous about doing this, because presenting math research is very different than just a simple presentation, because I'm trying to help you understand what this is so you can better appreciate it. So also, thank you guys all so much for listening. Raise your hand higher.
There you go.
Yes, Sarah.
All right. So what are some practical applications of this counting method?
Right. So combinatorics in general is most applicable in computer science, analysis of algorithms, and because that is becoming more prevalent in today's society, combinatorics is also a branch of mathematics that needs to be more prevalent as well. The goal of our research program was mainly just to shed light on this unstudied combinatorial object. So I'm not claiming there's going to be immediate practicalities of this, unfortunately. But another thing that should probably be noted is that when people do math research, it's not really for the goal of immediate practicality, right? You have people hundreds of years ago that are just like, hey, I got this math thing. What happens if I mess with it? What's going to happen, right? And they don't do that for the purpose of practicality. But then decades or maybe a century later, scientists come along and they're like, hey, we can use that, right? So I can't immediately tell you what the practicalities of this is, but it's very applicable in computer science, combinatorics is, and hopefully it'll be applicable later. So yeah. Yes.
So I was wondering, that you have the Moskins pass with the
Up steps.
up steps,
Yeah.
the
Level steps.
level steps, and then the down steps. Why don't you go down first? Why can't you go underneath?
Why can't you start by going underneath the axis?
Yeah.
Well, the definition of Moskins paths restricts it so that you can never go beneath the x-axis.
Okay.
That's also probably something I should have mentioned, that they're strictly above the x-axis, meaning that they can touch it, but they can never go below. So that's why you can never start with a down step, because you started with a down step, go beneath the x-axis, which we call no-no. So, yeah, Alex.
Same reason why you cannot go left.
Well, the reason why we can't go left is because all the steps that we have move the path one to the right. So there's not a single step that allows the path to move left, which is why it only stays positive, only stays in that first quadrant. That makes the Motzkin paths neater, so in an xy plane, Motzkin paths only exist in that first quadrant. Hi, Tika.
I missed what the T was in the A and Z sequences. Where is that on the...
Right, so the power of t represents, that's a bad example, where on the first row we are. So, for example, this z of t, we got 1 times t to the power of 0, right? Which means, if we do 5, for example, t to the power of 0 means we move 1 up for the z sequence, so we're doing 2. Plus t raised to the power of 1, meaning we move 1 over in our row. So that's 2 plus 3. The A sequence is a little bit different. We have 1 times t to the power of 0 means we move 1 up and 1 to the left on the triangle. So that 1 in the A sequence refers to the 2. If we're doing 9, 9 is 2 times 3 plus 1. And that power of t to the 1 means we're talking about the 3, and that t squared means we're talking about the 1. If that makes sense. This took me some time to understand as well.
So it's not a t isn't actually the value of t squared.
No.
It's telling you how to...
T doesn't have any value. The only reason why we care about t is so we know where on, we can put an exponent on it, and we know where on the row we are. It's the only thing we care about.
Thanks.
What would be the next row of that Pascal triangle?
Pascal's?
Yeah.
Yeah. That would be, anyone else want to shout it out?
I got 1, 6, 15, 20, 15, 6, 1. Is that correct?
Yeah. All you do to get Pascal's triangle is you just sum up the 2 elements of the row above it, and you just do that recursively.
Cool. Thanks.
Yeah.
All right, so join us for lunch. We'll be in the Joyce Room or the Corner Cafe. Otherwise, we'll see you all next week, Thursday.
If any of you guys are curious, this is my poster of all the results. All the results that we found. So if you guys are curious about that,